Hi, my name is Jack Barlow. I'm here to present my capstone project. For the past couple of years, I've been working on a capacitance bridge for measuring the density of states of two-dimensional materials. I've been working with Dr. Lu Li in the applied physics department, along with Cameron Zinn, a fellow undergraduate, and Eric Moilanen, who was an REU student that visited us for a summer and is now a graduate student here. So for a little bit of background about my project, basically in our lab, we focus on studying condensed matter physics. So physics at very small scales, very low temperatures, very low energies, where a lot of quantum effects start to show through in the devices that we're studying. Here we're studying semiconducting layers, so two-dimensional materials. They are atomically thin layers of materials that act as semiconductors. In our case, we're taking them and stacking them on top of one another, kind of like you would do when you make a parallel plate capacitor. Except in parallel plate capacitors, your two plates are made of metals generally, and they the electrons have conducting properties that allow them to be conducting at any energy. They just can move through the circuit freely. But in a semiconductor, the electrons are all subject to quantum effects, or well, more so. And there's a fixed number that can be promoted to the conducting band for every system energy, or it's determined by the Fermi level of your system. And this motion of high energy electrons in the conduction band and low energy ones in the valence band results in energy difference between plates of the capacitors that yields the quantum capacitance. This is different from geometric capacitance, like with parallel plate capacitors, where you take the area of the plates. This capacitance is due to the unique electronic transport qualities of these semiconducting layers. The actual quantum capacitance itself is directly related to this density of states function, which tells us how many electrons are in a conducting state as a function of system energy. So by determining the quantum capacitance through some kind of measurement circuit, we can determine the capacitance spectrum and then the density of states of the semiconductor device that we're studying. So our device that we're using to measure capacitance of these systems is called the capacitance bridge circuit. It looks like this. It contains a dual output function generator, which outputs the sinusoidal signals Vx and Vs. It contains a lock-in amplifier that reads the voltage at the point labeled null. It contains one standard capacitor, CS, that is something we know the capacitance of very well. And then we have our unknown device, CX. We balance the circuit, which means that we get it so that the null point has a voltage reading of 0 in both channels of the lock-in. So that means that both the real and imaginary parts of the voltage signal have been reduced to 0 at that point by adjusting Vx, by adjusting its phase and amplitude while holding Vs constant. And then once this bridge is balanced, this equation Vx equals Vs Cs holds, and we can solve for what Cx is based on what value of Vx satisfies the balancing point and the fact that we know Vs and Cs. So we wanted to do this. We have equipment around our lab to do all this, but we also were attempting to build a function generator for this purpose, and we did build a DC voltage source to apply a voltage to our sample to change the system energy. And then we're using a lock-in amplifier that we found in our lab. And all of these are programmable. So we want to be able to automate this process instead of having to physically adjust the voltages every time. We want it to just solve, have a program that solves for what amplitude does this correctly. So the way that we're doing that is using the bisection method, or the binary search algorithm, which applies normally to binary search trees, but you can also apply it to functions as well. Basically, we place a constraint on where we think the zero of the function might be, and then we iteratively reduce this search zone until we get to a point that reasonably contains the zero to a desired amount of accuracy. So that's how we find which values of the voltage and the phase cause a null voltage to read. We first adjust the phase of Vx by finding what phase causes the Y channel of the lock-in amplifier to read zero. Then we adjust its amplitude until we get the X channel to also read zero. Then we have both channels reading zero, then we know that our circuit is balanced. We wanted to extend this project once we have a working system and a program that automates the balancing to study the real effects of capacitors to just make sure that everything is as precise as we want it, and so that we have some real workable data. We will take, well, we do take two standard capacitors, two just metal capacitors, and make the circuit out of them. And we wanted to sweep through all possible frequencies of our output source and map the phase of that source as a function of that frequency when the circuit is balanced. Because when you have real capacitors in a circuit, they tend to exhibit a parallel resistive element, which dissipates some energy, and also all of your wires have some type of series resistance in them. So we model that using this circuit below, where we have a parallel resistance capital R for our capacitor and a series resistance R representing our leads. We expect to see at low frequency, low omega, we want a sharp drop off proportional to 1 over omega, and at high omega, it should be linear in omega. So we should see a quick drop off initially, and then steady rise in a linear fashion for higher frequencies. Once we have everything working, this Python program that we're using to perform all of these measurements will be made into a function that gets called by a Labview node. We're using Labview because much of the other stuff in the lab runs with Labview user interfaces. So that will just make things much more compatible with what we already use. And yeah, so the node will call the Python program that will send signals to our function generators, DC sources, lock-ins, and it will do the feedback loop using the bisection method to provide data for the Labview program. And quickly, I just wanted to answer some questions. So I got involved in this project when I was a sophomore. I've been working with Luli since November of 2018, I think. And I started working in the summer with him the following summer. This was the project that I was assigned. It had a lot of challenges. In that first summer, we tried using a different iteration of the function generator when I was trying to build the function generator. That didn't work. Then we had to switch to another one, which also didn't work. So in terms of challenges that I encountered and how I handled them, mostly it was about learning, when to kind of give up on things just when a project's really not working out. Those versions of the box really did not work. So we just ended up kind of settling to move on by using regular function generators that were around the lab and see what kind of results we could get from them. As for how I hope to use what I've learned for this project in my career, I'm going to be earning my PhD in physics at University of Washington starting this fall. So I hope to use this knowledge of programming equipment in my research. I hope to be able to use these kinds of ideas that kind of STEM in electrical engineering and apply them to the realm of physics in terms of being able to properly build equipment for measurements and like learn how data is quantized. I took several classes about signal processing for that purpose. So yeah, that's how I hope to use all these things. I kind of covered the challenges and how I handled them. As for where it's going, we want to make another function generator that will be more precise, hopefully, than the ones that we've been using. Our data isn't so great coming out the first time, but it does seem to be relatively precise, if not totally accurate. So it means that there's at least some consistency to the measurements that are occurring. They also will be putting the Python program that we've been using to, once it's made more accurate, that will be put into the Labview user interface. And then hopefully not long after, we can be doing these kinds of capacitance measurements for real samples. So yeah, so here are some references for the figures that I used throughout the presentation. And yeah, thank you very much for your time.